Hello everyone, I'm Pasindu and I'll present our work QuePaxa, Escaping the Tyranny of Timeout in Consensus. This work was done jointly with Cristina, Lefteris, Eva, Philipp, Vero and my advisor Bryan Ford. Suppose three replicas want to replicate state in a strongly consistent manner. They use consensus to have a totally ordered log. Even if minority of the replicas fail, replicas maintain the consistency. Consensus has been studied over 4 decades and it's also deployed in real-world systems. Having discussed the domain of our presentation, we first discuss problems we call the tyranny of timeouts in existing leader-based consensus protocols, and then we briefly discuss hedging and its relevance to QuePaxa. Then we present our now protocol and the experimental evaluation. We identify 3 problems in the existing consensus protocols because they use timeout for liveness: timeout-based view change, conservative timeouts, and manual configured timeouts. We refer these problems as tyrannies of timeouts. First, let us look at timeout-based view change problem. Assume a 4-replica configuration with R1 as the initial leader. All the replicas are in the view 1. Under good network conditions, the leader replica R1 proposes and the others will accept, and upon receiving a majority of the accepts, the leader will commit. As long as the network is synchronous, the leader will keep proposing and committing new commands. Now, let us see what goes wrong in the leader-based protocols. The leader R1 keeps proposing new commands in view 1. Due to a transient network problem, the leader replica becomes unreachable for the other replicas. Hence, they time out. Then the replicas go to view 2 and replica 2 starts a leader election protocol. This is called a view change. During the view change, no new commands are committed. We see that leader-based protocols need timeout for recovery. Hence, liveness depends on partial synchronous network conditions, which is problematic. Next, let us look at conservative timeout problem. It's difficult to choose an ideal timeout because it depends on many unpredictable factors. Since we cannot realistically get it perfectly, we have to weigh the risks of choosing the timeout too high or too low. Let us see what happens when you pick a timeout too high. Let us consider our previous example. When the timeout is high, replica 2, 3, and 4 wait for a longer period before initiating a view change. This results in high recovery time, which is not good for performance. Let us see what happens when you pick the timeout too low. In view 1, R1 is the elected leader. If R1 was not fail, but it is just slower than the timeout permits, then these timeouts cause the other replicas to ignore R1's message. Hence, replicas move to view 2 and R2 start a leader election. Low timeout cause other replicas to ignore R2's prepare and they move to view 3. This process can go forever without any leader making progress. Nothing is committed during the entire execution. Hence, we conclude that leader-based protocols have to sacrifice recovery time if they select a high timeout. If they select a low timeout, they risk sacrificing liveness. Finally, the third tyranny, manual configuration of timeouts. When the timeouts are selected manually, the protocol can stuck with a live but slow leader replica. Also, manual timeouts do not consider the dynamic network state. Having discussed the 3 tyranny of timeouts problems in this research, we ask, are timeout necessary for progress? We also ask, can we eliminate the impact of timeout for liveness? Now, there are asynchronous protocols whose liveness do not depend on the timeout. So, do they really solve our problem? Existing asynchronous protocols have quadratic or even cubic complexity, even in the normal case, hence inefficient than leader-based protocols under normal network conditions. Hence, they are rarely deployed. In this research, we asked whether we can have an alternative approach to consensus, such that the choice of timeout does not affect the liveness. Our envision approach is as follows. So, rather than a fixed leader, we assume there's a sequence of leaders. And under normal conditions, leader 1 proposes and the others will accept. If leader 1 is slow, then without a view change, then the leader 2 starts to propose and commit new request. If both leader 1 and leader 2 are slow, then after a delay, leader 3 starts to propose, but again without a view change. Our envision approach has a challenge. What if multiple proposers concurrently propose? Leader 1 initially proposes, and assuming that leader 1 is slow, leader 2 proposes concurrently. Can we support multiple proposals to be non-destructive? Our envision consensus protocol have some parallels with the technique we call hedging. So let us briefly look at hedging. Hedging is an existing technique that is used to curb the latency variability by issuing parallel requests. To illustrate, assume a two-tier architecture with server 1 in tier 1 and 3 stores in tier 2. To process a request, server needs to get a response from at least one store. The server sends parallel requests to multiple servers, assuming that at least one of them will respond quickly, and some stores responds to the request. When server receives multiple responses, they do not interfere with each other, and this is the key idea of hedging. So we ask, can we apply hedging to consensus such that concurrent proposals do not destructively interfere with each other? With that, we are ready to explore QuePaxa, our novel algorithm. QuePaxa makes the following contributions. It's a consensus protocol that eliminates the tyranny of timeouts problem for liveness. It's the first consensus protocol to support hedging in consensus. It's a novel consensus protocol that is as good as the existing leader-based protocols under normal case network conditions, while providing robustness against adversarial network conditions. This is a mini roadmap for our QuePaxa discussion. We first give you an operational overview of QuePaxa. Second, we discuss abstract QuePaxa, which is a simplified version of QuePaxa for ease of understanding, and we discuss its safety and liveness properties. And then we show how we convert this abstract QuePaxa to the concrete QuePaxa protocol. In QuePaxa, each replica plays two roles: proposers and recorders. The recorders are passive memory units and they store the state. The proposers are active and they drive the consensus by sending RPCs to recorders. Submitters or the front ends submit commands to the proposers. Like Paxos, QuePaxa runs the protocol for each slot, where a slot is a consensus instance. And each slot contains multiple rounds, and within a round, there are 4 phases. In a given round, QuePaxa has 4 phases. In phase 0, the proposers flip a coin and assign a priority to their proposals and send the proposal to all the recorders. Then in phases 1 to 3, each proposer propagates the learned values from the recorders. The proposers decide in 2 occasions. In phase 0, if the network is synchronous and only one proposer is proposing, and second, at the end of the second phase with some probability. Having seen the architecture and the protocol overview, we now discuss abstract QuePaxa protocol, which is a simplified version of QuePaxa that is used for illustration purposes. Any asynchronous protocol has to solve 2 main challenges: replica failure challenge and network asynchrony challenge. As a first step, let us assume that the network is synchronous and solve only the replica failure challenge first. And the resulting protocol is what we call the abstract QuePaxa. We assume a primitive called threshold synchronous broadcast, a novel network abstraction that we propose in our paper, that provides the lockstep synchrony to the consensus layer. Abstract QuePaxa uses randomization to prioritize proposals, and it uses 3 T-cast or threshold synchronous broadcast steps. The point here is that it's a conceptually simple protocol that I'm going to explain in the next few slides. We said that we rely on tcast to abstract away network asynchrony. Let us see what tcast gives us. Each node proposes a value. For example, Alice proposes A, Bob proposes B, and Charlie proposes C. They use tcast to distribute the proposals and learn of other proposals. The first property of tcast, each node learns a majority of the proposals. For instance, Alice learns A and B, Bob learns A and B, and Charlie learns B and C. The second property of tcast, each node learns a proposal that all nodes know to exist. For example, after this tcast call, all Alice, Bob, and Charlie learn that all other nodes know that proposal B exists. In general, tcast doesn't provide any guarantee that nodes learn the same set, so we haven't solved the consensus problem yet. Sets from one tcast invocation are insufficient for consensus. Using multiple tcast calls, each node approximates what other nodes know about these sets. Therefore, we use 3 tcast calls to achieve the following. All nodes learn 3 sets: existent, common, and universal. If Alice knows that a proposal exists, it's in her existence set. If Alice knows that all nodes know a proposal to exist, it's in Alice's common set. If Alice knows that all nodes know a proposal to be common, then it's in Alice's universal set. The key relationship that enables QuePaxa to reach a consensus decision is this inclusion relationship. This means any node's universal set is included in any node's common set, which is in turn included in any node's existence set. This is a visual depiction of the set relationship. First, each node forms the existence sets, then the common sets, and finally the universal sets. Any node's universal set that we depict in green is a subset of any node's common set, depicted in orange, which is a subset of any node existence set, depicted in blue. The figure shows that the sets of each node are not guaranteed to be the same. However, even with this imperfect knowledge of different sets, nodes use the inclusion relationship to reach consensus, as I'm going to explain next. Now let us see how QuePaxa reaches a safe decision. A node proposes a value and disseminates it in 3 tcast rounds. The decision condition is that the best proposal in the existence set is also the best in the universal set. Suppose Alice is lucky and her sets fulfill the decision condition. Then she decides on the best in her existence set. Now assume that Bob cannot decide. Then Bob proposes in the next round its best proposal in the common set. So let's see why this is a safe decision. Value selected by Bob necessarily equals the value Alice might have decided. Since all users that could not decide do that, the only possible decision going forward in the next rounds is the value that Alice decided. Therefore, we claim that abstract QuePaxa ensures safety. Now let us quickly see how nodes decide in expectation. The probability that Alice decided is that the best proposal in her existence set equals the best proposal in her universal set. And here are the node sets. Each set, by construction, have at least majority of the proposals. And we want the best proposal to be in the universal as depicted. The probability is at least half in expectation. Therefore, each node decides in 2 rounds in expectation. To summarize the abstract QuePaxa algorithm does not depend on timeout for liveness, and it's robust against adversarial network conditions. However, abstract QuePaxa has quadratic message complexity, and hence it's slow under normal case executions. Finally, abstract QuePaxa does not support hedging, which is our main motivation for looking at a new protocol. With that, let us briefly look at how we convert this abstract QuePaxa algorithm to a concrete QuePaxa algorithm. Abstract QuePaxa algorithm assumed a tcast primitive, and it solves only the reliability problem. In the concrete QuePaxa, we replace this tcast layer with a proposer algorithm that uses a very simple atomic accesses to a new kind of atomic register that we call interval summary register. The concrete QuePaxa has linear overhead under normal case network executions. It's robust and it supports hedging. and it's also implementation ready. To remind you about the architecture of our concrete QuePaxa, each replica plays two roles, active proposers and passive recorders. So let us briefly see how these two components work. Recorders implements what we call an interval summer register. An interval summer register uses a threshold logical clock or a step counter to handle network asynchrony. Our interval summer register is a constant space and records the summary of values submitted in the current and the previous steps. Please see the paper for more details. This is the proposer code. Basically, it invokes the interval summer register in the recorders in 4 phases using RPC. Finally, let us recap how QuePaxa built a consensus scheme that allows hedging. In phase 0 of a round, one or more proposers propose for the same slot. In phases 1 to 3, each proposer propagates the information recorded in the recorders. Even when more than one proposer is active, they do not interfere with each other. Hence, QuePaxa support hedging because multiple proposers do not cancel each other. We make tuning and performance optimizations in the paper, and please refer the paper for more details. Finally, let us look at the evaluation. In this evaluation, we ask, can QuePaxa guarantee liveness under any timeout? Under normal case executions, how does QuePaxa compare with leader-based protocols? Under adversarial conditions, does QuePaxa provide liveness? And finally, can QuePaxa converge to the best hedging sequence automatically? We experimented in AWS AC2, both in a local area network and a wide area network. This graph shows the impact of timeout for liveness. In the x-axis, we show the lead timeout for Paxos and Raft and the hedging delay for QuePaxa. In the y-axis, we show the throughput. QuePaxa is live for any hedging delay, but in contrast, Multipaxos and Raft are live only when the lead timeout is greater than the network round-trip time. Hence, we claim that QuePaxa supports low hedging delays without sacrificing the liveness. The second graph measures the overhead of QuePaxa when the hedging delay is less than the network round-trip time. In the y-axis, we show the average number of steps per slot that represents the additional bandwidth overhead of QuePaxa. We observe that only when the hedging delay is less than the network round-trip time, QuePaxa has additional overhead due to redundant proposals by concurrent proposals. The third graph shows the impact of timeout for recovery. In the y-axis, we show the recovery time. We see that QuePaxa has a low recovery time, but in contrast, Paxos and Raft have significantly high recovery times. Now, let us look at the normal case execution. In this graph, we compare the normal case performance of QuePaxa in a wide area network against the existing protocols. In the x-axis, we show the throughput, and the y-axis depicts the median latency. We see that QuePaxa performs comparable to Multipaxos, which is an existing leader-based protocol. This graph shows the throughput versus latency behavior of QuePaxa under adversarial network conditions or under asynchronous network conditions. We see that QuePaxa remains live under adversarial network conditions, but in contrast, Paxos and Raft, they lose liveness when the network is adversarial. So in conclusion, we presented QuePaxa, a novel randomized protocol that eliminates timeout from liveness guarantees, and it supports hedging. QuePaxa provides multipaxos equivalent performance on normal case, and it's resilient to asynchronous network conditions. Our work is publicly available in GitHub. Thank you.
Hi, Harold Ng from KTH. Thanks for your talk. I was wondering, usually when you have protocols that support multiple proposers, you need a super quorum in the fast phase and then a normal quorum in the recovery phase, let's say. Does QuePaxa use a super quorum in the fast phase? And if not, how does it avoid it?
By super quorum, you mean more than a majority?
Yes.
So to come up with a totally asynchronous protocol, you don't have to use a super quorum. You can still do it with n minus f number of replicas or number of nodes in the asynchronous path. But I think you are referring to protocols like EPFL, where they have this special fast path that uses a supercorer.
I was thinking more towards fast Paxos.
So fast Paxos, yes, they use a majority quorum because, first of all, it's not an asynchronous protocol. It just has this fast path because they can avoid going through the leader. But in QuePaxa, we support the fast path and also the slow path just by using the majority.
Essentially, the question is, what happens if a proposer, let's say, fails before it manages to commit? How does the nodes afterwards manage to recover his value that he tried to propose?
Right. So this is what I showed you. Yeah. So I'll explain using this slide. So in the first path, let's say proposer 1 initially proposed a value and he was idle. No other proposer was there. So let's say along the way he failed, he did not commit, he just proposed. So in QuePaxa, what happens is the secondary leader will come without view change and he will first look at the recorders and see if there are any decision that I should go and commit. So what happens in that case is if there is a stale value that is from a previous proposer, then the secondary leader will actually go ahead and commit that value using the next 3 phases.
So I guess, let's say proposer 1 manages to, the message reached recorder 1 and recorder 2,
Correct.
while proposer 2 managed to reach recorder 3, right? So it can happen in a majority, you see
Yes.
like 2 values.
Yes.
Is it then tie-break by this priority?
So, yeah, that's a good question. Now, if proposer 1 is lucky enough to get into a majority of the recorders, then with high probability, we say that it can commit in the fast path, 1 network round trip path. However, due to ordering of messages by the network adversary, it's possible that they can go to slow path and commit in the slow path. But if, just to highlight what you said again, if proposer 1 if the proposer 1 can reach the first 2 recorders and replicate its value, then he will succeed in the fast path, but not the proposer 2 who only succeeded in getting his value saved in only 1 recorder.
Okay, thanks.
Thank you.
One more quick question.
Hi, so Yash Gupta from UC Berkeley. Thanks for the talk. I want to know is that the key motivation for the paper is that timeouts are hard to determine and we don't know how to calculate them, right?
Right.
But hedging believes on time delay.
Right.
So time delay again means you have to somehow measure time delay. There's a way how proposer 2 can know that proposer 1's value it has not reached, right?
Right.
So isn't time delay same as timeout?
Right, that's a very good question. So we call it hedging delay versus timeout. So just to illustrate, timeout initiate a failure recovery process. What I mean by that is, when you initiate a failure recovery process, you are going to actually stop what you are currently doing. Just to illustrate, assume a raft protocol execution. Now, if there's a view change, which is the failure recovery of raft, then it's going to actually halt the progress of the current leader. Now, what's different with hedging and why we use hedging delay instead of timeout, it's not a failure recovery mechanism. It's a non-destructive concurrency mechanism where even if the proposer 2 comes to the picture while the proposer 1 is still active, they do not destructively interfere with each other. So that's the key difference between timeout in multiplexers and raft and hedging in QuePaxa.